For nearly 1 billion years, an immense geological fracture has rested beneath the center of North America, concealed under forests, highways, cities, farms, and the cold, dark waters of the Great Lakes. It stretches in a vast arc from present-day Kansas through Nebraska, Iowa, Minnesota, beneath Lake Superior, and into Michigan, forming one of the largest ancient volcanic structures ever discovered on Earth. Most people living above it never feel it. Many have never heard of it. Yet scientists continue mapping it, scanning it with seismic instruments, measuring its magnetic anomalies, and tracking subtle earthquake activity linked to faults that formed when the continent nearly tore itself apart. Now, renewed scientific attention is focusing on a difficult question that has begun appearing more often in geological research papers, seismic studies, and mineral exploration programs. Why are some portions of this ancient system showing signs of renewed stress deep underground? Why do small earthquakes continue appearing near sections of a structure believed to have died more than 1 billion years ago? And why are researchers increasingly describing the Midcontinent Rift system not as a completely dormant scar, but as a buried weakness that still influences the behavior of the North American crust today? The Midcontinent Rift system is not a volcano waiting to erupt. It is not a modern plate boundary like California's San Andreas Fault. No evidence suggests North America is preparing to split apart again through the Great Lakes region. Yet the structure beneath the continent remains so enormous, so geologically unusual, and so physically influential, that scientists are continuing to reassess how deeply it still affects the modern landscape above it. Its dimensions alone are staggering. The rift extends for roughly 1,200 to 1,900 miles, or approximately 2,000 to 3,000 kilometers, depending on the interpretation and mapping method used. In some places, volcanic rock associated with the rift reaches thicknesses of nearly 18 miles, or close to 30 kilometers. These volcanic accumulations were created during an extraordinary period of tectonic upheaval roughly 1.1 billion years ago during the Mesoproterozoic era, long before dinosaurs, mammals, flowering plants, or even complex multicellular life populated Earth's surface. At that time, the ancient North American continent, known to geologists as Laurentia, was undergoing extreme internal stress. Deep beneath the crust, enormous volumes of superheated mantle material began rising upward. Scientists believe this upwelling weakened the crust from below, producing a gigantic continental rupture that opened across the middle of the continent. Massive fractures formed. The crust stretched and sagged downward. Lava surged upward through fissures in repeated eruptions that continued for millions of years. The scale of volcanism was almost unimaginable. Floods of basaltic lava spread across the landscape in successive eruptions, building immense volcanic plateaus layer by layer. Some lava flows traveled enormous distances before cooling. Entire basins sank under the weight of accumulating volcanic material. Deep grabens formed as blocks of crust collapsed inward between major faults. Sediments later poured into these depressions, burying portions of the volcanic terrain beneath thick layers of younger rock. Had the process continued long enough, North America might have split into separate landmasses. A new ocean basin could have formed through the center of the continent, similar to the way the Atlantic Ocean eventually opened hundreds of millions of years later. Geological evidence suggests the Midcontinent Rift advanced far enough that complete continental breakup was a genuine possibility rather than a minor tectonic event. But the process stopped. Why it stopped remains one of the central questions in North American geology. Researchers generally connect the rift's failure to massive tectonic collisions occurring east of the developing fracture during the Grenville orogeny, an immense mountain building event that reshaped the eastern margin of ancient North America. As continental masses collided, compressional forces overwhelmed the stretching forces driving the rift. The crust stopped pulling apart. Volcanism diminished. The fractures ceased widening. Over time, the failed rift cooled, hardened, and became buried beneath younger rock formations. Instead of becoming an ocean, it became a scar. That scar still dominates the geology of the Great Lakes region today. Lake Superior itself exists largely because of the ancient rift. The deep basin beneath the lake follows part of the old tectonic depression formed during continental stretching more than 1 billion years ago. Much later, glaciers deepened and sculpted the region during repeated ice ages, carving the modern lake basin into the volcanic and sedimentary rocks left behind by the rifting process. The dramatic cliffs along portions of Minnesota, Wisconsin, Michigan, and Ontario reveal black basalt formations created directly by those ancient eruptions. In the Keweenaw Peninsula of Michigan, layers of volcanic rock tilted during rifting remain exposed at the surface. In northern Minnesota, gravity surveys reveal dense volcanic accumulations hidden beneath younger terrain. Magnetic anomalies associated with iron-rich basaltic rock stretch across large portions of central North America, allowing scientists to trace the buried rift even where no visible surface expression remains. These magnetic signatures are so large that they were among the earliest clues revealing the true scale of the structure. Long before modern seismic imaging existed, geophysicists noticed strange magnetic patterns running across the continent. Aircraft surveys later confirmed that massive quantities of volcanic rock were concealed beneath sedimentary cover. Eventually, seismic reflection studies beneath Lake Superior revealed thick volcanic sequences filling deep, asymmetric basins associated with the ancient rift zone. The more scientists studied the structure, the stranger it appeared. The Midcontinent Rift was not a narrow crack. It was an enormous tectonic system involving huge magma volumes, major crustal thinning, widespread faulting, and volcanic output comparable to some of Earth's largest known flood basalt provinces. Certain estimates suggest the total volume of erupted material reached levels comparable to major volcanic events associated with continental breakup elsewhere on the planet. Yet despite its immense size, the system effectively froze in place. For generations, geology textbooks often describe the Midcontinent Rift as ancient and inactive, an extraordinary but finished chapter in Earth's tectonic history. In broad terms, that remains true. The rift is not reopening. No credible evidence suggests magma is rising beneath the Great Lakes in a way that resembles active volcanic provinces. But modern seismic monitoring has complicated the older idea that the system became completely irrelevant after its collapse. Small earthquakes continue occurring near portions of the ancient structure. Most are minor. Many are too weak to be felt by humans. Yet they continue appearing across regions influenced by old rift faults and associated crustal weaknesses. Parts of Minnesota, Wisconsin, Michigan, and surrounding areas occasionally experience measurable seismic activity tied not to active plate boundaries, but to stress redistribution within the North American plate itself. This distinction matters. North America is often perceived as tectonically stable away from the West Coast, but the continental interior is not completely motionless. Stress from plate interactions along distant margins can still travel through the crust. Ancient faults, especially large buried structures like the Midcontinent Rift, may serve as zones where that stress becomes concentrated. Scientists studying intraplate earthquakes increasingly examine whether old tectonic scars continue shaping modern seismic behavior long after their original activity ceased. The New Madrid seismic zone farther south offers another example of this phenomenon. There, powerful earthquakes struck the central United States during the early 19th century along ancient buried faults within the continental interior. Although the geological settings differ, both regions demonstrate that ancient tectonic structures can remain mechanically important for immense spans of time. In the Great Lakes region, seismicity remains far weaker than major active fault systems elsewhere in the world. Still, the persistence of earthquakes near portions of the rift has encouraged deeper investigation into how ancient crustal structures interact with modern stress fields. Advanced seismic imaging technologies are now allowing researchers to study the crust beneath the Great Lakes in far greater detail than earlier generations could achieve. Networks of seismometers can detect subtle waves traveling through buried rock layers, helping scientists reconstruct the geometry of ancient faults and volcanic accumulations deep underground. Gravity mapping continues refining estimates of volcanic thickness and crustal density variations associated with the rift system. Researchers are also examining how the ancient structure influences groundwater movement, heat flow, and mineral formation. The mineral wealth associated with the Midcontinent Rift is enormous. During the active volcanic phase, Circulating hydrothermal fluids moved through fractures within the crust, concentrating economically important metals in certain regions. Michigan's famous native copper deposits formed through these processes. Large copper sulfide deposits in Minnesota also originated from rift-related geological activity. Today, growing global demand for critical minerals used in batteries, electrical infrastructure, and advanced technology has intensified scientific and commercial interest in the region. Copper, nickel, cobalt, and platinum group elements associated with portions of the rift have become strategically important resources. Exploration programs continue re-evaluating ancient geological formations, once studied primarily for academic purposes. Some researchers believe additional undiscovered deposits remain buried beneath sedimentary cover along portions of the system. The renewed focus on critical minerals has indirectly driven new geological research into the structure itself. Modern airborne magnetic surveys, deep seismic studies, and drilling programs are producing increasingly detailed images of crustal features hidden for hundreds of millions of years. Another emerging area of interest involves natural hydrogen. In recent years, scientists worldwide have begun investigating whether certain geological environments naturally generate hydrogen gas underground through chemical reactions involving iron-rich rock and water. Because the Midcontinent Rift contains extensive basaltic formations rich in iron-bearing minerals, some researchers believe portions of the system may possess conditions favorable for natural hydrogen generation. Interest in naturally occurring hydrogen has grown rapidly as nations search for low-carbon energy sources. Unlike industrial hydrogen production, geological hydrogen could theoretically accumulate underground through natural processes over long periods of time. Research into this possibility remains in early stages, but the ancient volcanic rocks beneath the Great Lakes have become part of the discussion. The idea that a billion-year-old failed rift might someday contribute to future energy development would have sounded improbable only a few decades ago. Yet the Midcontinent Rift continues surprising researchers precisely because of its unusual preservation and scale. Many ancient rift systems elsewhere in the world were heavily deformed, destroyed, or obscured by later tectonic events. The Midcontinent Rift survived within the stable North American craton, allowing large portions of the structure to remain comparatively intact beneath younger rock layers. This preservation makes it one of the world's most valuable natural laboratories for studying the early stages of continental breakup. Scientists can analyze volcanic sequences, fault structures, sedimentary basins, and crustal architecture representing a tectonic process that almost succeeded but ultimately failed. Few geological features preserve this intermediate stage so clearly. The Great Lakes region therefore occupies a unique position in global geology. Beneath an area associated today with freshwater resources, shipping corridors, forests, and industrial cities lies evidence of one of the most dramatic tectonic episodes in North American history. The physical effects remain visible across the landscape. The rugged volcanic terrain surrounding parts of Lake Superior differs sharply from many surrounding regions because of the ancient basaltic formations produced during rifting. Gravity anomalies continue influencing regional geophysical measurements. Buried dense rock masses alter magnetic readings across wide sections of the continent. Fault systems created during crustal stretching still shape the architecture of underground rock formations. Even erosion patterns and topography in some areas reflect the deep geological inheritance left behind by the failed rift. Far beneath the Great Lakes, the ancient rift continues influencing the structure of the North American continent in ways that are often invisible from the surface. Modern cities rise above it. Freight corridors cross it. Pipelines, rail networks, and electrical grids span terrain shaped by geological forces older than complex animal life itself. Yet even after more than 1 billion years, scientists still do not fully understand every process that occurred during the formation and collapse of the Midcontinent Rift system. Part of the difficulty comes from the sheer scale of time involved. Human civilization occupies only a microscopic fraction of Earth's geological history. The rift formed during an era when the planet looked radically different from today. North America existed as part of an ancient supercontinent environment. The atmosphere contained different oxygen levels. Life remained largely microscopic in the oceans. No forests existed, No birds crossed the skies above the volcanic eruptions. No grasslands covered the lava plains. The eruptions themselves may have transformed enormous portions of the landscape into volcanic deserts dominated by black basalt flows, fissure eruptions, ash deposits, and collapsing fault valleys extending for hundreds of miles across the continent. Some researchers believe volcanic gases released during peak eruptive phases may even have influenced global climate conditions during portions of the Mesoproterozoic era. The lava sequences produced during the rifting episode are among the thickest continental volcanic accumulations ever identified in North America. In portions of the Lake Superior region, stacked basalt flows preserve evidence of repeated eruptions over immense timescales. Some individual flows traveled extraordinary distances before cooling and solidifying. In certain exposed outcrops around Lake Superior, geologists can still observe structures formed as ancient lava cooled. Columnar jointing, mineral-filled cavities, and tilted volcanic strata remain visible reminders of the tectonic violence that once reshaped the center of the continent. These formations are not isolated volcanic remnants. They are fragments of a gigantic continental-scale rupture system that nearly altered the entire geography of North America permanently. The more researchers study the rift, the more evidence they find that the process approached true continental separation before failing. Seismic imaging suggests major crustal thinning occurred beneath portions of the rift zone. In some locations, the crust may have been stretched close to its structural limit. Massive intrusive bodies of magma solidified underground while surface eruptions continued above. The total amount of magma emplaced during the event was so large that parts of the crust became substantially denser than surrounding regions. That density difference still matters today. One reason the Midcontinent Rift can be mapped so effectively beneath buried terrain is because the volcanic rocks produce unusually strong gravity and magnetic signatures. Basalt contains abundant iron-rich minerals capable of generating magnetic anomalies detectable even where the structure lies deeply buried beneath younger sedimentary layers. Geophysical surveys have revealed these anomalies extending across enormous portions of central North America. The buried arc beneath Lake Superior remains especially prominent, but the structure continues southwestward beneath states where almost no surface evidence is visible to the public. To many residents above the rift, the landscape appears geologically ordinary. Farms stretch across the plains, suburbs expand over buried volcanic rock, rivers cross ancient faults without revealing the tectonic history below. Yet hidden beneath these modern environments lies one of Earth's largest preserved failed continental rifts. Scientists increasingly view ancient structures like the Midcontinent Rift not as completely dead systems, but as inherited weaknesses embedded within the continental crust. This concept has become increasingly important in modern tectonic research. Continents are not perfectly rigid blocks of rock. They contain zones weakened by previous tectonic episodes, ancient mountain-building events, long-extinct fault systems, and buried rifts created hundreds of millions or even billions of years earlier. These inherited weaknesses can influence how stress travels through the crust long after the original tectonic event ends. In the case of the Midcontinent Rift, ancient faults may still affect the distribution of modern seismic stress throughout portions of the continental interior. Researchers studying intraplate earthquakes continue examining whether small seismic events near the Great Lakes region correlate with buried rift structures formed during the original extension phase. Most of these earthquakes remain relatively minor. Still, their existence demonstrates that the crust above the ancient rift is not entirely inactive. In Minnesota, small earthquakes have occasionally occurred near buried portions of the structure. Michigan and surrounding regions have also experienced low-level seismic activity tied to ancient fault systems. Canada's side of the Lake Superior Basin likewise contains faults associated with the old rift architecture. These earthquakes are generally weak compared to major tectonic zones around the world, but they carry scientific significance because they reveal where stress continues interacting with ancient crustal structures. Some researchers suspect the enormous contrast between dense volcanic rock within the rift and lighter surrounding crust may also influence how seismic energy propagates through the region. The physical properties of the buried volcanic material differ substantially from surrounding formations, potentially affecting wave behavior during earthquakes. This ongoing research has practical implications beyond academic geology. Understanding buried crustal structures helps engineers evaluate seismic hazards, infrastructure stability, and subsurface resource development. Although the Great Lakes region is not considered a major earthquake zone, even moderate seismic events can pose risks in areas where buildings and infrastructure were not designed with strong earthquake resistance in mind. The ancient rift also influences groundwater systems and subsurface heat distribution. Deep fractures associated with the rifting process can alter fluid movement through underground rock layers. In some locations, mineral-rich fluids continue circulating through old fault zones. These interactions partly explain why economically valuable mineral deposits became concentrated in certain regions linked to the rift. The Keweenaw Peninsula's copper deposits remain among the most famous examples. For thousands of years before modern industrial mining began, indigenous peoples extracted native copper from the region using stone tools. Later, during the 19th century, industrial mining transformed portions of Michigan into major copper-producing districts. The source of that copper traces directly back to hydrothermal processes associated with the ancient volcanic system. Superheated fluids circulated through fractures in cooling volcanic rock, depositing copper minerals within veins and porous formations. The resulting concentrations became economically important on a global scale during the growth of industrial civilization. Modern exploration companies are now re-evaluating similar geological environments associated with the Midcontinent Rift, as global demand for copper and battery-related minerals accelerates. Copper has become increasingly essential for electrical infrastructure, renewable energy systems, electric vehicles, and large-scale power transmission. Nickel and cobalt associated with certain rift-related deposits are likewise considered strategically important materials for modern industry. This renewed economic interest has produced another wave of scientific mapping across portions of the ancient structure. Airborne geophysical surveys now generate highly detailed magnetic and gravity datasets capable of imaging buried formations with remarkable precision. Deep drilling projects continue recovering rock samples from portions of the rift hidden beneath younger sedimentary cover. Sophisticated computer models simulate how magma moved through the crust during the original rifting episode. Researchers are also studying why volcanism became so intense during the formation phase. One leading explanation involves mantle plume activity, where unusually hot material rose upward from deep within Earth's mantle. This heat weakened the crust and triggered large-scale extension. However, scientists continue debating whether plume activity alone explains the rift's evolution or whether broader tectonic forces within the ancient continent also played major roles. Some models suggest the rift formed during a period when tectonic stresses were already affecting Laurentia on a continental scale. Others emphasize the extraordinary volume of magma as evidence for deep mantle processes driving the event from below. The debate remains active because the Midcontinent Rift occupies a unique geological category. Unlike modern active rifts, such as the East African Rift, scientists cannot directly observe the process unfolding in real time. Instead, they must reconstruct events using buried rock layers, geophysical imaging, mineral chemistry, structural analysis, and ancient volcanic sequences preserved across the region. Each new dataset adds detail to the reconstruction of a tectonic episode that unfolded over immense spans of geological time. The structure's preservation beneath the stable North American craton is one reason it remains so scientifically valuable. Many ancient tectonic zones elsewhere on Earth were later destroyed by mountain building, subduction, or repeated continental collisions. The Midcontinent Rift survived comparatively intact because the interior of North America remained relatively stable after the rifting event ended. That stability effectively locked the ancient structure into place beneath the continent. Yet stable in geological terms does not mean motionless.